In this example, we've got a W 14 by 82 steel beam, and directly the problem statement asks us only to calculate the Q, capital Q, that goes with the first moment of an outward area that's associated with transverse shear stress, right? And they ask us to do it at different locations, and then find the transverse shear stress across the cross section if the internal shear is of a specific value. So let's hit the question about the first moment of outward area first, and then we'll get into the other aspects of the problem, right? Now, you might find it a little difficult to see what we've got here on the page. The 14 by 82, we look up and we find out its depth or height is 14.31 inches. Then the flange width is 10.14 inches, and the flange thickness is 0.855 inches, right? Those are really small numbers there. And then the overall stem thickness is at 0.51 inches. So let's repeat that over here, because that will be helpful for us as we're trying to figure out what's really going on in this problem statement about what it's really asking us to do. All right, so I'm going to redraw the overall cross-section and then relabel various parts. There's our flange, and the bottom flange will be over here. All right, so there we've got our basic W14 by 82. Its width is 10.14 inches down here. Its total height is 14.31 inches, and then the thickness of the web 0.51 inches, and then the thickness of the flange will be 0.855 inches. Those are theoretical numbers that we use for design calculations. When it's rolled, it'll be a little bit different than that. That W14 by 82, remember that 14 refers to the approximate height or depth of the cross section. 82 refers to the weight of this cross section in steel in pounds per foot, so 82 pounds per foot, right? And that's what our given here is. Our find then is the Q at various locations, right? And tau equal VQ over IB. We're asked to find it at the outer fiber, and then at the web flange intersection, and at the neutral axis, right? Now, at the outer, that would be at distance C from the neutral axis. Well, the neutral axis is, of course, located dead set in the center of this thing because of its symmetric nature. We don't have to prove that. So it's here at the mid-height. So our C value then, I'm going to go all the way up to that top. Our C distance would be half of the height. So about 7.15 inches would be our C value. Right now, notice that in that case, our value of Q, then that's that first moment of that area, that Y bar of that special area, and then times that area itself, right? Well, that distance all the way to that outer would be our 7.15 inches. It's a rectangular area that has width of 10.14 inches, but being all the way out that outer piece, there is no real rectangle that we're working with. That's going to be 0 inches, so the Q value is 0 for that one. Right? So that was one of them that we're supposed to find. The other one is at the web flange intersection. So let's go take a look at what's going on with that one, right? So now in that case, we're right here at this little location, right? Boom, right there. That's where we're at. So the area that we're talking about is this outboard area right there, right? So there are QW flange being that first moment of that area. Well, the area is that rectangle, right? And that rectangle is 10.14 inches wide by 0.855 inches high. Then we got to get its moment arm, right? Well, its moment arm is to the centroid of that little piece, right? So if we go the C distance of 7.15 inches, and then we come back down, half of this 0.855 will be where we want to be. And that actual net distance would be 7.15 minus 0.5 times the 0.855. That'd be 6.72 is what that is, right? That value is for that moment arm. Times the 0.855 times 10.14, and we get a value of about 58.3 cubic inches, right? Hey, let's check to see if they agree. Somebody agrees with us. Yay, cool. And then we want to get it at the neutral axis, right? And so let's go find that one. And so Q at the neutral axis, right? So that's going to be the first moment of this area. Well, that's all of this area. We can either go all the top or we can go all the bottom. I'm going to show it as though we're doing all the bottom stuff. Remember, it's not going to matter. We're going to get the right answer either way. And that little T that's there can be broken into two pieces, one on the flange, which we just calculated at 58.3, right? That first moment was with respect to the same axis we're going there, so that number hasn't changed. So then we just got to get this little piece here, right? And so its moment arm is half of the point. Oh, wait a minute. No, it's not. Sorry. The width of that is 0.51. The height of that rectangle is, oh, this is nasty, right? So we got to go up or down, whichever way you want to look at it. The 7.15 come down 0.855. So the height of that rectangle, 7.15, that's half of the 14.31. 51, sorry, still not right. 7.15 minus the 0.855. So that height is 6.295. That's the rectangular area. And then its height, its centroidal distance is half of that. So we multiplied by half of 6.295. That's what all that turns out to be the same as. And so now let's do the calculation. So that latter part is 5.15, add it to the 58.3, and you get 63.45, or about 63.4. You really should round down that 5 to the even number always. And what do we get here? 68.4 cubic inches. Somebody doesn't agree with us. So, well, maybe that 3 should have been an 8. Let's go and double check the numbers here and see where we might have made a mistake, or maybe it's a typographical mistake. You never know. Right? We know the 58.3. We agree with that. So this is all about this web portion that we haven't grabbed. So let's be real careful about that. 14.31 is the overall height. The distance from here, the neutral axis, to the outer is half of that. So that's the 7.15. And if we weren't right, we wouldn't have gotten this other information correct. So I'm okay with the 7.15. Subtract off the 0.855, and that leaves us with 6.295. So I'm okay with that. So that area then is 6.295 times 0.51. The area of this little piece of the stem is 3.21. And we're going to multiply it times half of that height, and we get 10.1. I think I made just a calculation here when I entered this to begin with, plus the 58.3. So now we get 68.4, which I can cleverly just turn into that 3 into an 8. I'm going to double check it one more time just for the heck of it. So 0.51 times the height squared, divide that by 2. Yep. I just made a calculation error before, and we get the 68.4 correct. Okay, good. So that's the variation in the Q as we march from the outer to the flange intersection down to the neutral axis. Now let's go find out what the stress values are at these various locations. Right? So we are also given that our shear demand is 200 kips. And so we're going to also find taut at C, taut at the web flange intersection, and taut at the neutral axis will be the other quantities that we're going to do. So taut at C at the outer fiber, well, it's going to be 0. But why? Well, that's because taut equal VQ over IB, and Q is 0. So therefore, at point C, that is, taut C equals 0. So that was a sort of easy one there. Right? Now, for taut at the web flange intersection, we actually going to have two answers, right? Because the value of B, the width, changes depending on if we're up into, just barely into the flange or only in the stem, right? So taut web flange at the web, again, it's going to be VQ over IB, and our shear is 200 kips. Our Q, capital Q, is 58.3 cubic inches. We're going to look up the second moment of area, or we'd have to calculate it doing all those rectangles, but we look in the back of our textbook and we'll find that that second moment of area for W14 by 82 with respect to the x-axis is about 881 inches to the fourth. And then if we're up into the web, then that width is the full 10.14 inches. So 200 times 58.3 divided by 881 divided by 10.14, and we get a stress of 1.3 KSI, right? But if we are then, so that's just up into the flange. If we're into the web itself, then everything changes except for the 10.14. Sorry, everything stays the same except for that. And so we've got the 200 kips times our 58.3 over our 881, and that is no longer 10.14, but it's the width right here, that point, which is the 0.51, right? That's going to dramatically go up by almost a factor of 20, right? It's going to be the ratio of these two, because everything else is the same, so I'm not going to work it all the way out. If you want to, go ahead. But that equals 29.95, so round that to 26.0 KSI. Right? So notice a big change, all because that width there changes so significantly. Right? So then I'm going to have to sort of wrap the page around a little bit here. Right? So then we'll find taut at the neutral axis. And same formula, VQ over IB. The shear is the same. The Q has gone up to 68.4 cubic inches over our I value, and our width is 0.51 inches, right? So then we'll have 200 times 68.4 divided by 881 divided by 0.51 equals then 30.44, or about 30.4 KSI for the maximum stress. Now, how that's going to look on the cross section is we got a piece of everything's rectangular in nature, right? So there's the edge of your cross section, right? There's your flanges running. So we're seeing the side of the beam now, not the cross section itself. And our shear stress distribution, which we know is parabolic in nature, is going to start at 0 at the outer edge. It's going to have a sudden change right at the web flange intersection, and it will be maximum at the neutral axis, which is, of course, located in the center of this thing. And so note we've got 30.4 out here. and then parabolic variation right down to there at the 26, and then it will then jump down to the 1.3 and then go to 0. So there's a parabolic variation there, parabolic variation to 0 there, sudden discontinuity there, and then get my little template out to do the curve with a maximum right there in the center. And that'll be, of course, parabolic overall. And that's what the shear stress distribution would look like for strong axis bending and the shear that's going in the perpendicular to the x-axis. It's parabolic variation with those kinds of values for 0 out here at the outer edges.